Hi friends, today we are going to basically look at alpha decay equations. We are going to learn how to write them and balance them. But before we do that, we need to first know what an alpha particle is, because all reactions that involve alpha decay involve emission of an alpha particle. When you look at a given atom that has a very large nucleus, like in this image, this is a nucleus of a given atom and it contains very many neutrons and protons. The essence of radioactivity is for these atoms or elements to become much more stable. As a result, some of them release particles, alpha, beta, and gamma, and this aids them to become much more stable. So in this case, we have a nucleus. It has very many neutrons and protons, and it spits out or removes or emits 2 protons and 2 neutrons in the process. And these 4 subatomic particles that are being emitted, it's what we call the alpha particle. The removal of 2 neutrons and 2 protons in the process. So that's all about what an alpha particle is. So alpha decay will basically involve an atom that's unstable, tending to release an alpha particle so that it gains stability. Scientists haven't discovered as to why these atoms undergo this kind of decay, because considered random or spontaneous. We don't have a good reason for it, but basically we know is that it's all about attaining stability. We are going to start with uranium-233 and see what happens when such an element of uranium undergoes alpha decay. But before we have a look at that, we need to first know the atomic notation. Have a simple reminder. We shall realize that when writing an atom, we shall always put a subscript to represent the atomic number on the left-hand side of the chemical symbol, while the superscript will always represent the sum of protons and neutrons, also known as mass number or atomic mass. So when you look at uranium-233 undergoing alpha decay, we shall realize that we shall need to first know the number of protons and number of neutrons in this element. So we shall write N and P so that we can be able to follow the number of protons and neutrons. In this case, we shall see that the number of protons will be 92 because this is the atomic number. Number of protons is atomic number. So uranium-233 has atomic number 92, and then the number of neutrons will be the mass number minus the atomic number, giving us 141 number of neutrons. So our uranium has 141 neutrons and 92 protons. So the new element that will be formed will have 2 protons less and 2 neutrons less. Why? Because the alpha particle will go with the other 2 protons and 2 neutrons. So our new element will have 92 minus 2, which will give us 90, because the other 2 protons have been removed by emission of this alpha particle. As well, the number of neutrons will also decrease by 2 to get 139. That is after subtracting 141 minus 2. So here all you need is to be able to read the periodic table, go to the periodic table and try to identify which element has atomic number 90. Don't look for mass number, look for atomic number. So when you go to our periodic table, you shall realize that the new element will be thorium 90. So this will be our new element when uranium undergoes alpha decay. Yes, obviously this is named after Thor, the god of thunder. So we shall see thorium as our new element. That means whenever uranium-233 undergoes alpha decay, a new element known as thorium will always be formed. However, in the periodic table, you'll find it under actinides, the lowest part of the periodic table. That's where you'll find your thorium. So we shall have to write it on the right-hand side of the arrow, because that's where we have the products. Then plus our alpha particle, which is a helium nucleus. Just that maybe it has no electrons, but helium nucleus, 2 protons and 2 neutrons. And it will give us a mass number of 4, because 2 neutrons and 2 protons will give us a 4. So in this case, we shall also get our mass number for thorium by just adding the number of neutrons plus the number of protons. And this will be our alpha decay equation. Uranium undergoing alpha decay by emitting a helium, positively charged helium atom, or we can say a helium nucleus together with the new element being formed. Let's have a look at another example whereby probably we start with the products and want to identify which element underwent that kind of alpha decay. Yes, alpha can be written like this because it was the first element that was discovered, and following the Greek alphabet, alpha comes as number 1. So let's have a look at the second equation. We don't know the element which underwent alpha decay, but at least we know the products whereby we have the alpha particle being emitted, at the same time a new element Pa or protactinium that is being formed in the process. So we have a new element Pa with atomic number 91, and alpha particle was also emitted. What could have been the element that underwent this kind of radioactivity? So in this case, we need to first know the number of protons and neutrons for the products. Alpha particle shall have 2 neutrons and 2 protons. Neutrons are always got by subtracting the mass number minus the atomic number. So 4 minus 2, we get 2. While protactinium, number of protons will be 91. We shall follow the subscript, while the number of neutrons will be the mass number 233 minus 91, and we shall get 142. But now we should know that the product or the substance actually that underwent this kind of decay must have had 2 more protons and 2 more neutrons. So we shall just have to do some simple math and add 2 neutrons to 91, sorry, 2 protons to 91, and then 2 neutrons to 142. And when we do that, we shall realize that we shall get 93 as the number of protons and 144 as the number of neutrons. So all we need to do is follow our periodic table and look for which atom will have atomic number 91. And then we shall realize that it's Neptunium 237 that will have atomic number 93. So our new element, or the element that underwent this kind of alpha emission, will have been Neptunium after Neptune. So we shall realize that it's not that complex writing this kind of equations, but all you need to know is being able to balance number of neutrons and number of protons. Unlike the usual chemical equations, whereby we normally balance the number of atoms in that equation, in this case, we basically balance number of protons or atomic number with the mass number. So we shall get 93 and 237. So this is all about alpha decay. So in simple terms, we shall realize that whenever an element undergoes alpha decay, for example, Neptunium in this equation underwent an alpha decay, we shall realize that we will have reduced in terms of mass number by 4. That's why we are saying mass number will reduce by 4. That is -4. Or we shall have the atomic number decreasing by 2 from 93 to 91. That's a decrease of 2. So by knowing this, we can always easily foretell the product formed or the substance that underwent this kind of decay without writing this kind of notation. Yes, without following maybe NP numbers. So in this case, we shall have a look at 2 equations. We shall start with polonium 208 undergoing alpha decay. Obviously, if it undergoes alpha decay, we must have the alpha particle on the right-hand side of the arrow, because that's where we have the products. So we have alpha particle being emitted, but we want to identify what is the product. So here what we shall need to know is that when 2 neutrons and 2 protons are removed, 84 minus 2, these 2 that are part of the alpha particle, we shall get 82. So 84 minus 2 is 82. So the new element must have atomic number 82. So we shall have to go to the periodic table once again and find which element that is. At the same time, the mass number will have to decrease by 4. So 208 minus 4, we get 204. So the new element having atomic number 82 will be lead and will have mass number 204. And that's how we shall be able to tell which new element will be formed when polonium 208 undergoes alpha decay. So it will be lead 204 that will be formed. So always in these equations, make sure that the number of protons and the mass number are always equal. Before and after, they should always be equal. 208 for polonium, 204 plus 4 is 208. 84 polonium, 82 lead plus 2 in the alpha particle, which is 84. So before and after should always be equal. Then lastly, in this case, we are going to start with the products. We don't know which substance underwent this kind of decay. So we shall start with ruthenium, Ru, atomic number 86, mass number 218, with the alpha particle obviously being emitted. So feel free to pause the video and try out and see which element or which atomic number must have undergone this kind of decay for ruthenium 218 to be emitted, to be formed with emission of an alpha particle, as I give you a couple of seconds. Yes, thank you. I believe you are able to find out. Simply you have to follow the rule that the mass number will always decrease by 4 and atomic number will decrease by 2. So if the atomic number is 86, that means the element that underwent this kind of alpha decay must have had 86 plus 2, which is 88. While the mass number will have decreased by 4. So 218 plus 4, we shall get 222. But most importantly, for us to know the element, because it's the atomic number that always determines the type of element. So 88 is what we shall look for on the periodic table to identify the element that will be formed. And we shall realize it's radium as the element that underwent this kind of alpha decay. As simple as that, you can be able to tell which elements underwent alpha decay and which element was formed as a result of alpha decay. So this is a brief video on how we can write alpha decay equations. In our next video, shall have a look at how we can write beta decay equations. Yes, thank you for watching. See you next time.